Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Syarul Aziz bin Hamidin. My number entry is CN200105. So I'm going to present about IoT Smart Greenhouse. So this is my overall system block diagram, which is the main uh, microcontroller, which is Raspberry Pi, connected to DHT22, TSL2561, MH, Z19B, and Atlas Scientific Probe. That is the sensors with the output going to Blue Lab Guardian Monitor and ThinkSpeak. Next, IoT taxonomy. I use five sensors, which is number one is temperature DHT22, that is to detect humidity and ambient temperature. Light intensity sensor, which is the TSL2561, that is to optimize lighting conditions for plant growth and adjust artificial lighting if needed. Carbon dioxide sensors MHZ19B, to provide real-time data on CO2 concentration, helping optimize ventilation and ensure sufficient CO2 for photosynthesis. pH sensor, which is the Atlas Scientific pH probe, is to monitor the acidity and alkalinity of the hydroponic nutrient solution. And lastly is the electrical conductivity sensors. Blue light guided monitor is to measure the conductivity of the hydroponic solution, providing an indication of its nutrient concentration. Next is pre-processing. I use the main controller, which is the Raspberry Pi. The ARM-based CPU of the Raspberry Pi provides enough processing capacity to meet the needs of the smart greenhouse system for data processing. It has Wi-Fi and Bluetooth built-in, enabling easy access to other devices and data transmission or remote monitoring via internet. USB port allow addition of numerous peripherals such as cameras and sensors. Type of data being collected and data processing in the Raspberry Pi. Temperature and humidity sensor can record raw data in the appropriate sensor specific units. Data filtering techniques can be used by the microcontroller to eliminate noise and outliers from the acquired data. The microcontroller ability is to restore the gathered data in a local database, enable quick access to historical information for analysis or producing reports. Through Wi-Fi and internet connections, the microcontroller can link into the cloud or central server, enabling data transmission for additional analysis, visualization, or remote monitoring. Next, communication. In this greenhouse, we use the Wi-Fi and Bluetooth. So the Wi-Fi offers a fast and dependable wireless connectivity. It enables seamless communication between the microcontroller and other components such as the sensor actuator and or centralized server. And Bluetooth technology works effectively in this project. It makes it possible for close-by gadgets such wearable tablets or smartphone to connect and communicate with the system. So the middleware is the ThinkSpeak. ThinkSpeak is the real-time analytics and data visualization tools are provided by ThinkSpeak for collection of sensor data. Using API key, data from the microcontroller can be uploaded to ThinkSpeak. The sensor data is included in the HTTP push request for that the microcontroller sends to a specific channel on ThinkSpeak. The data then is then timestamped and stored by ThinkSpeak, enabling user to build a unique dashboard, examine the data, and get alert in response to predefined threshold. Application. So this is my application in the smartphone using the ThinkSpeak. It displays real-time reading from sensor in the form of graph with the temperature, humidity, and carbon dioxide readings. By clicking on the appropriate sensor, user can choose which sensor data they want to have display on the interface. Greenhouse for farmer, real-time sensor data and equipment status in the dashboard, adjust environment parameter and manage irrigation and nutrient delivery for controlling, receive alerts for critical condition or equipment issue, and lastly is access historical sensor data and generate reports for performance evaluation. That is all for me. Thank you very much.